All right, we left off with timing jitter. We're going to have short-term and long-term jitter. What the heck is jitter? Well, it's an undesirable shift. What does it mean by a shift? Well, that's your ping rate, gentlemen. When you are playing a game and you see your ping rate go through the roof, that's a timing jitter. Now, some, are brief. Sometimes you can recover in your game. And then there are some times where you can't recover, and by the time you get back in, the game has dropped you off and you're dead, or whatever, your tank is destroyed or whatever. So you have short-term jitter. Now this one I like to describe as when you go to YouTube or Netflix and you see that little circle all of a sudden pop up there before the video starts. What it's doing is buffering. And that buffer normally is called an elastic store when we talk short-term jitter. What it's doing is it's gathering the information, figuring out when would be the best time to start playing the video to where you can watch it in its entirety without the audio and the video not being in sync. Bye. No? Maybe?
Ha!
Oh, come on. You don't like that?
Sir, that was a good one. That was a good one, sir. Don't worry.
Yeah. Anyway, the
Bye.
yeah. The elastic store is what you see is the buffering. When we look at long-term jitter, this one is because of the unsynchronized clocks. It happens all the time out there. The question is whether or not it loses timing and how long it loses timing before they sync back up. Now, how do they sync back up? Well, phase-locked loop. Because the distant end is always going to have a delay getting to where it needs to go. For example, I explained to you earlier that UTC, when it gets to USNO, there's a lag time of milliseconds. Milliseconds is pretty big. Microseconds, and then we get into nanoseconds, which is a little bit more acceptable. Now, with phase-locked loop, what they do is they take those two clocks, compare them, and then they resync everything back up to where everything normalizes. That's how you're able to play games. For example, if I want to go play on the European server for World of Tanks, I have to get their synchronization with my particular devices here in the house. Of course, it has to go through servers and everything else, and that's how it syncs up. And normally there is you can tell it at times, there is a very small lag time between when you're pressing the button to, let's say, shoot at someone or go forward or go back. It gets to be a little difficult because there is a ping. It's not as bad as the Russian server, which is, it's really bad on the Russian server. So you get pretty lucky every now and then if you get a good ping rate from here in the Russian server. And that's on War of the Tanks. Just saying. So you can see the synchronization between the clocks in order to play these games. There are 4 different types of network synchronization. We got the Isochronous, the mutual, master clock, master slave. I always call Isochronous the dinosaur. Makes it look so much more elegant to say, ooh, Isochronous. Now, what does it do? Well, each node produces its own clock, but it uses an elastic store between them. They're pretty much a self-contained unit, kind of like when you linked up 2 computers together. That's one way that they're able to sync up, is using that elastic store. And you can play games between each other, download files or whatever. I wouldn't recommend playing games. And of course you have mutual. That one is more set up for if you guys decide to do what's called a LAN party over there in the dorms. It does average all the clocks together. It does sync everything else. the nice thing about this one is if one of the guys or girls decide, hey, I'm tired, I'm going to go to bed, and they unlink their computer from all this LAN party stuff, then it's no big deal. It just takes a couple seconds for everything to sync back up. Master clock, this one is where I like to reference it to what happened if the master clock fails. The master clock distributes time to everything else, but if it fails, everything fails. Back in my day, we had bells in our high school. Bells are all linked to the master clock in the principal's office. And then one day, the principal's office clock failed, which meant every clock in the classroom stopped. It was about 2 weeks before they got the master clock fixed. So you can imagine it's a little confusing, but the secretary normally is pretty good about getting on, everybody synced up on the correct time. Hey, it's that time, everybody changed, and this is going out over the intercom system we had in the school. Yes, 1978 was a long time ago. And then we have the master slave. Now this one is what DoD uses. And the way this one works, normally we have a master clock. If that master clock, another one takes over and everybody resyncs the time to the master clock. The idea behind this is called redundancy. So, for example, if we are in a world time situation and the enemy takes out a couple of our bases and one of them happens to be the main time for everybody, another base will take up the time and redistribute it and get everybody synced back up. So we've gone through purpose of timing, timing standards, timing sources, time coordination distribution agencies, timing jitter, network synchronization. So when we look at timing sources, what is the most accurate timing source there? Juarez?
I'm sorry, sir. May you repeat that?
Sure can. What was the most accurate timing source that we have out there?
Is the HIPAA?
Well, that's where all the timing, reference is coming from, but what does it use in order to keep time?
If I can phone a friend,
Yeah, go
I
ahead.
would like to do so.
Ring.
UTC? Is that
Negative.
what I heard?
What is UTC to keep time?
Is that atomic time?
Yeah, there we go. Atomic time. It uses two atomic oscillators we talked about. What are they? Mills?
The two for atomic are oh my bad. The two for atomic are ribulum and cesium.
That is correct. What's the least accurate time? Marshman? Least accurate timing source.
Quartz.
Stevens.
Is it quartz?
Yeah. All right, Senior and Bell.
Good
What
answer, Marshall.
were
Thank you, Thomas.
two timing jitters that we talked about? Senior and Bell?
Right, I just got here. So I can only talk to my phone. It was like on the other side of the room.
Okay.
But two timing jitters. I'm not quite sure. I can't remember.
Thomas?
This is one I can't really remember.
You said timing jitter,
It
correct?
was just short term and long term, right?
Yep. Short term and
Oh,
long
it
term.
is. Got it.
Quinnes. Senior McQuinnes, can you tell me what the short term uses to keep its time? Short term. Go ahead and type it in chat. No idea there, Senior McQuinnis?
Wait, what's used to
What's
create
used
it or counteract it?
counteract it? Steven, stay until he can at least type it in or at least say, I don't know.
Sit.
Stay, boy, stay.
Hold your horses.
I don't know. Okay, Stevens, go ahead.
Okay, I got it. So to counteract short-term jitter, we use what was it?
Flex
Store.
Flex seal.
Elastic store.
Store.
Okay,
Yeah, flex
Elastic
seal.
store.
Yes.
So, Mills, what do we use for long-term jitter and to get our clock synchronized?
Phase lock loop.
Okay. What were the 4 network synchronization types? Juarez?
I know it's master slave, master clock, and then mutual, and that P word.
Yes.
Dinosaur.
Good.
Dinosaur one.
Good.
Isochronous.
Fantastic. So we're going to go to the next objective, 1 Bravo. So what does this mean right now? It means that you guys will have to do all of 1 Alpha for homework that will be due on Monday when we finally get back to class. So to see how that's going to work, if we complete 1 Bravo, then we will have all of 1 Bravo to do. But if we do not finish it, then there is a very good possibility that you need to go ahead and start on it to finish it up when we finally do.
So you said finish up 1 Bravo?
We're wanting to finish 1
Start.
Bravo for the day. Okay, if
Yes,
we
sir.
finish 1 Bravo, then 1 Bravo will be due. If we don't finish it, I'm recommending that you try to go ahead and get as much as you can done on it.
Do you have another class to teach later?
Negative. I can go until 8 o'clock tonight.
Let's do it.
Okay. Identify the relationship of basic facts, state general principles associated with the principles, capabilities, limitations of multiplexers. Just remember, you got to get a 70% on the test. What does that mean? It means that you can only miss 12 out of the 40. Get that 70. We're going to be looking at the AFSC applications. The bottom line is you will have to touch a multiplexer. You're going to be doing it with the NSM50 for the next couple days. We're going to go through general multiplexing terms, input data relationships, types of multiplexing, modes of TDM, demultiplexing, signal formats, analog digital conversion. Now, most of this is generalized information, so bear with me on this. So what are the terms? Analog and digital. So let's go with Marshman. Read those two, please.
Analog. An infinite number of values with constantly changing amplitude. And digital, a limited number of values, either a logic 1 or a logic 0.
Now, Juarez, do you know what it means?
Can I take a guess?
Go ahead.
Well, I mean, the analog says, I feel like analog just goes by amplitudes, and digital just goes by 1s and 0s.
Yep.
So I guess analog goes by, you know what, I don't even know.
Well, you were on the road. Pretty good. So the way I like to look at analog and digital is analog's all over the place. So what does that mean? It means it's infinite. It means that it's constantly changing, unlimited. And another electronic word called indiscrete, meaning those 3 terms. If you know that, then digital's the opposite. So yeah, digital is limited, it's finite, it's discrete. So those are 3 words for those 2 particular terms. You know
So
one?
I would have thought that digital would have been infinite because it's kind of easy.
Run that by me again there.
I would have just thought the digital would be the infinite one, just based off like the logic of thinking of digital things being more efficient than analog.
Normally, digital is more efficient than analog in some ways. There are advantages and disadvantages with the two. Analog, you can hear my voice, but it's not going to be the same all the time. It's all over the spectrum. That's the reason why they classify it as infinite. Digital, it's either it's a 1 or it's a 0, and normally it's described with voltages being the normal area is from 0 to 5. So that's the reason why that is limited. So next up we have bit. You guys have worked with this in block 6, correct?
Yes, sir.
Yes, sir.
Okay. Bit versus byte. You get into that discussing. So what is multiplexing? The bottom line here is you've got 2 or more channels. I don't like to use users because you can have multiple users on one channel. It is a composite signal that's coming out or an aggregate. When we look at the information on this particular one as far as a pictorial view, you can see that we have number 1 is diagonal lines, number 2 is a solid bar, and number 3 is horizontal lines. You can see with each one of them, it starts with channel 1, goes to channel 2, channel 3, and then back up to 1, 2, 3, 1, 2, 3. And you can see that the first time it went through, that would be frame 1, and we'll get into this in just a little bit. Frame 1 consists of channel 1 first, channel 2 second, and channel 3 third. You should not see these things jumbled up. If they get out of sequence, you're going to have problems with your timing. Sampling. This one is talking about when we look at an analog signal, converting it into a digital one, we're going to take samples off of that waveform. They're going to be equal as far as distance between each of the samples, and it's going to be in a logical step. When I take this, and most people will go from right to left. I'll explain this in just a minute. You'll notice that this space between here and here is the same. Here and here is the same. Here and here is the same. But you notice that where we take these samples, the sample is different. This is how our CDs, MP3s, MP4s, and so forth and so on are now done, is we convert the analog and put it into a digital format now.
So it's basically just grabbing it at different spots.
Yes. But again, each one of those samples is the same distance, and we'll get into how they do it when we get into the analog and digital formats. Frame. Remember I talked about this just very briefly at the front end of that multiplexer. This is a sample from each channel. The idea behind this is to make sure that you are in sequence. If it gets out of sequence, at least if I go frame 1, somehow got in between frame 2 and 3, then at the distant end it should be able to figure that out. Hey, I need to get frame 1 back in sync with it. And it could cause problems if you don't have highly synchronized clocks. When I say clocks, using phase lock loop.
Is that exclusive to video?
No, it is not exclusive to video. You got data of all different types going through. There's different ways the data comes down the line, and we'll get to that in just a few minutes as to something called asynchronous, synchronous, and isochronous, and how that gets it from point A to point B. You have non-information bits. This is not part of the intelligence. What does it mean by the intelligence? Well, if you got an 8-bit word, that's considered the intelligence. What goes before it, what goes after it, is considered the non-information. In other words, not part of the intelligence. Examples of this are framing bit, start bit, stop bit, and stuffing bit. We'll get into each one of these a little bit later. We have bandwidth. This is another way of saying, hey, this is how fast I am, this is how much space I'm using, or it's a range of frequencies. Here we go. Async. This is how computers work. The bottom line is it does take up more bandwidth than synchronous does, and I'll get to that in just a minute. Why? Because not only does it have a framing bit with it, but it also has stop and start bits. So it tells you where to start the word and where to end the word. That's the reason why they're called non-information bits. Synchronous, however, is a fixed rate. The way I like to describe this is channel 1 all the way through how many channels you have. Every one of them has a set time to get data or to put data on the stream. If you don't have anything in there, that's time that is wasted. I'll explain a little bit more on that. Isochronous, this is async at a synchronous rate. What does that mean? It means that I'm still sending stop and start bits where I didn't have to do it with synchronous, but it's done at a synchronous rate, and if I don't have anything to fill that place up, then I got to stuff it like a turkey. Got to put stuffing in the turkey. And that helps it with being able to sync up everything where it doesn't get off time. Now, the way I like to look at this is I run a 16 camera system on my house here, and it toggles through every one of those cameras, so I can see video, and if I got audio connected to it, it toggles through each one of them. And that's because it's a synchronous signal, but it's an async signal because it's so different each time it sends me more information. So I could get a car passing by, or I could get somebody singing when they're going by the sidewalk, so forth and so on. But it toggles through each one of those cameras in recording them, if I wanted to do it that way. Normally I have all 16 cameras to come up, and it shows everything and anything I need it to. The best place that I know of for a little bit better as far as Air Force would be what's called a WSA. You guys know what a WSA is?
I do not.
Weapons Storage Area. It could be small, it can be huge, depending on what base you're going to. They use the isochronous. Why? Because not only do they do video, they do audio, and they do a bunch of sensors, motion sensors, vibration sensors, and so forth and so on. So this would be an example of how it's being used out there. A lot of information coming down the line for that alarm indicator, so to speak. We have FDM, that's frequency division multiplexing. The big thing on that one is frequencies. This is what I like to describe as the earlier cell phone systems. You can see with user A, we have 82 to 83 gig. User B is 83.1 to 84 gig. User C is, or Charlie, is 84.1 to 85.0 gig. Let me try to explain this to you. What does that mean? It means that when I open up my cell phone and I start dialing in, it's going to secure one of those particular sites with that particular frequency. And it's going to use it and send it down the line to whoever needs to be, that you need to talk to. The problem is if you are on a cell site doing this, that's basically where you're going, and you go from one cell site to the other, what happens if, let's say, you're on user A, alpha, and you go to the next cell site and all the channels are being used, what's going to happen? You're going to get dropped. Whereas nowadays they have a way which is using TDM, where they use time, whereas if you got on that certain frequency, it's going to find a time to put you on to send your information. So it's a little bit different. Now with the TDM, what that does is it goes through a lot more channels than this, but it gives you an idea how everything is fractioned up into each of the frame. Frame 1 shows you channels 1 through 4. Frame 2, same thing, over and over again. The idea behind this is you've got a particular time to put your information in. We have synchronous and asynchronous for modes of TDM. Synchronous assigns time slots, and you can see that last one, which I've been telling you before, wasted time bandwidth. Wasted time and bandwidth. Ridiculous. It only uses frame bits, and the reason why it uses frame bits is because you don't need to know how to start the word or stop the word, because the frame does that for you. Synchronous time, as you can see with this particular one, you can see here for each of the channels. So for the first one, Alpha Bravo Charlie Delta is being used. Frame 1, Alpha Bravo Charlie Delta is being used. Here's your frame bit. And then we get to the second frame. There's your frame bit to start us off. We have Alpha Bravo, there is no Charlie, and then a Delta. You can see that because we don't have anything to put in there, that's wasted time. We go to frame 3, framing bit, Alpha. We don't have anything in Bravo or Charlie. Again, that's wasted bandwidth. And then we get to frame 4, which is Alpha. That's all that's in there. So you waste time with Bravo, Charlie, and Delta. Then we get to async. This one assigns time slots only to the active channels. In other words, if you're on it, you get to use it, but just remember there are some advantages and disadvantages to it. So let's take a look at it. It is multiplexer efficient, and let me explain. Just like before, you had Alpha, Bravo, Charlie, and Delta in frame 1. The problem is you're going to have a frame bit, a start bit, a stop bit, so forth and so on. When you get to frame 2, this is where you start seeing a little bit more of your speed and bandwidth being able to increase. So you have Alpha, Bravo, there is no Charlie, and then there's Delta. Again, we're still going off of these. You have frame 3, which is Alpha and Delta. Notice we don't have a Charlie or Bravo in there, so you're starting to speed up even quicker. And then you get to frame 4. Wow. Boy, it really sped up quick, didn't it? Now, with this one, our computers use this. And if you hadn't noticed, during the day when you get in the dorms, you're probably saturated as far as the multiplexer and the server is concerned when you're dealing with the internet in your dorms, correct? Help me out here.
Absolutely.
Okay, so with that in mind, when you guys get further in time, let's say about 8, 9 o'clock tonight, the speed starts changing, doesn't it? You're able to get on and play a little bit easier, and you get the ping rate down, and you don't have that lag that you used to have at 4 or 5 o'clock in the afternoon, do you?
Right.
So this is the reason why, is this synchronous time rate, asynchronous time rate, is because when less people are on it, you have the better chance of being able to get a larger portion and quicker portion of that bandwidth. Asynchronous transmitted at a large rate here. You can see that the frame bit, start bit, stop bit in between your 8 bits of data. And then of course when you get into here, the nice thing is Charlie's missing. So again, it just shows you the non-information bits compared to the data. When we get to asynchronous transmitted and asynchronous rate, better known as isochronous, or isochronous is another one. This is where we have to stuff the area where we're missing. How many people have watched the movie Tron Legacy?
Yes, sir.
That was
I
pretty
have.
good.
What was Cora?
A robot.
Oh, she had a name.
Or
Yep, Cora, the female. Okay, she's the one that rescued Jeff Bridges' son from the games and programs. Notice that games and programs, they developed something. Yes! ISO. She was an ISO. Get it? Isochronous. Yeah, now you're going to have to go back and watch that. Ding, 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 ding. Okay.
So why did they call her ISO specifically?
That's because games and programs, they're working off of synchronous and asynchronous. Developed an ISO. If you listen to Jeff Bridges talk about it, you will see that when they were using those two devices together with Clue, and then this thing happened called ISO. Remember? And that's how Cora got
so she
developed.
just got put in.
No, she was ISO is one of those things that you know, because you combine those two devices together, you know, asynchronous with asynchronous rate, it's a different product out there, and it uses a ton of overhead. Now, what is overhead? It's non-information bits. Why? Because you're not only dealing with stuffing bits and everything else with the start and stop and framing bits. It's a lot of information, so you have what's called overhead. Overhead is the non-information bits. We also had things like forward error correction, interleaving, and so forth and so on. So there's a lot more to it than meets the eye. Demultiplexing. The easiest way to describe this is if it works in multiplexing, you have to do it in demultiplex. Well, what does that mean? Okay, if you encrypt in multiplex, you should be able to decrypt in demultiplex. If you have
So it's on the receiving side.
yeah, demultiplex is the receive side. Multiplex is the transmit side. Think of it this way. I always equate multiplexing and demultiplexing with modulation and demodulation. It works similar. Works similar. Just a tad bit different in the way we line things up. Let's talk signal formats. Oh boy, here we go. There are three types that we look at. One is called non-return to zero. We have a return to zero and something called conditioned diphase. The first two that you can read online, not a problem. It's when you get to conditioned diphase that you will see either Manchester diphase, which is the earlier form of CDI, or differential diphase, which is a derivative of Manchester but is considered CDI. Now, here's the fun part that I always like to challenge you guys with. When you read this, and I'm going to go through this real quick, how do you read it? Left to right, right to left? Anybody?
Left to right.
Left to right.
So that's a general consensus, left to right?
Yes, sir.
Mega.
You sure?
Ones, tens, 100,000, 10,000, 100,000, million.
And which way are you reading it?
That was Hebrew style.
Mm-hmm.
So right to left.
Yes. Anytime you're dealing with numbers, it's always the least significant digit to the most significant digit. That's how we always deal with numbers. Digital is no different. Analog is no different. It is, and I'm going to put this out here. We, as humans, always like to say we're going to read from left to right. It's natural because that's the way we're taught. With numbers, it works differently. Now, with that in mind, when you go and look at, let's say, signal formats, you have to figure out what the individual or what the article is referencing, because sometimes they will reference the numbers from left to right. Those are the ones that are not what I call electronic savvy. The ones that are electronic savvy will always do it from right to left. So if you were to read an article on Manchester diphase or differential diphase and look at their numbers from, let's say, Wikipedia, they're going to say it from left to right, and somebody from an electronic website will go from right to left. I'm putting that out there because there are differences. And I'm trying to explain to you that, okay, how's the article going? You're going to deal with this out there in the tech order or tech manual world. So when you're looking something up in your tech order or tech manual and you got to go to the internet to look it up, please try to understand what the tech order is saying versus what that website is saying. I know it's convoluted in a little bit, but I see this a lot when you start looking at information and trying to decipher it. This goes for 8-bit words and the way we do what's called clock cycles. In the signal format world, we work off of clock cycles in order to get the format correct. The 8-bit word that we deal with, you can see the first set of numbers 1 through 8. The bottom set of numbers 1, 2, 4, 8, 16, 32, 64, 128. We're going to come back to this in a little while. Our clock cycle always starts from right to left, because when you get ready to send it out as an aggregate, you're going to see that first number on the left-hand side. That's the least significant digit being sent to the distant end. The first number they're going to get is the least significant digit. Let's get through each one of these signal formats. You got non-return to zero. There's two different types, neutral and polar. It is the most common format in a multiplexer. So if you're dealing with the NSM50, and I challenge you with this, take a look at the computer when you're putting in your information and see if you can't find NRZ. I'll guarantee you will if you know where to look. Normally it's on the first window that you open when you start inputting everything in. I think it's the bottom right hand side, and I think it goes to NRZ and CDI on it. Again, most common format in a multiplexer. I don't know of any other format multiplexer that does not have this in there. What does it do? It doesn't return to zero halfway through the clock cycle. We'll get to that in just a second. Two different types, neutral and polar. So let's take a look at each one of them. Neutral means that a +5 is a logic 1, a 0 is a 0. Short cable runs. The last sentence is important. Actually, the last 3 words, not self-clocking. I'll get to that in just a minute. What does it mean by that? Let's take a look at the data format here. Okay, first of all, we have the clock cycle coming in telling us how we have to put our format together. We get the data that's coming in, the ones and zeros, let's say, from a computer. Now we got to make a signal format in the NRZ neutral waveform. So we get a 0. We start at 0. At 0 volts plus 5. For 0, halfway through the clock cycle, nothing happens. We get a 1. It rises to plus 5. Halfway through the clock cycle, non-return to 0. So you can see how this is a play on words. So 1s will always be plus 5. 0s will always be 0. This is a reason why this is considered not self-clocking. It won't become evident to you until I do show you a self-clocking signal format. Okay. Again, we always have a clock cycle. We have the data coming in. This is our signal format that we're going to send to the dissonant. This is polar. Again, we have plus 5 for 1s. The difference will be a negative 5 for a 0. This section right here, you can run on longer cables. And then the last part, not self-clocking. There's not much difference between neutral and polar on NRZ other than the voltage difference. You have 10 volt difference versus 5 volt difference. You can use a longer cable run. This is the same data that we had before, so nothing really has changed except the digital signal has become, the difference of potential has become 10 volts instead of 5 volts. Now what does that mean on a long cable run? Well, if you had a 5 volt difference, as you start going out further and further, you have this thing called resistance of the cable. Well, if you had a 1, which is a 5 volt signal, sent to the dissonant and it's too long, you're probably not going to get a difference. Let's just say that by the time it gets to the dissonant, instead of being a 5 volt, it might be 1 or 2 volts. Well, it doesn't see it as a 1. It'll probably think it's a 0, so you can see how that would be a problem. Whereas the polar signal has 10 volts difference of potential. So if you see it at a 1 or a 2, more than likely it's going to say, hey, this is definitely a logic of 1 versus, you know, a negative 5, let's say a negative 2 or 3, you're going to see a difference of potential between the two. So that's the reason why you can run polar farther than you can neutral. Let's look at RZ. That's return to 0. We have 4 of them: neutral, polar, bipolar, and bipolar with 0 suppression. This returns to 0 halfway through the clock cycle. Halfway through the clock cycle. There you go. So we have 4 in RZ. Neutral, again, plus 5, 0. Not self-clocking. Short cable runs. Same thing as neutral, or excuse me, RZ, NRZ, neutral and polar, just a tad bit different on polar. Neutral, pretty much the same thing, except for when you look at the ones, halfway through the clock cycle, it's going to return to 0. Here's another data of 1, halfway through the clock cycle. It's going to return to 0. Get it? Return to 0. But you can see why this is not self-clocking, because it doesn't look anything like our clock cycle, does it? RZ polar. This one Logic 1s are +5. Logic 0s, -5. Both return to 0 halfway through the clock cycle. Hence the words return. Oh, look at this. Self-clocking. Let's look at this. You have a 0 for your data. Here's your clock. What happens? The 0 goes to -5 because that's what we logged it in as. Zeros, -5. Halfway through the clock cycle, it does something and comes back to 0. Let's see the 1. Okay, halfway through the clock cycle, it returns to 0. Notice every single piece of data, it's doing something halfway through the clock cycle. Guess what just happened?
Not just after a 5-0, but after everything.
Everything. Zeros are -5. +5s are the logic 1s. Zeros are -5. So with that in mind, something is happening halfway through the clock cycle. This is a reason why I don't have to send additional information down the road. And you're going, okay, I don't understand. When you are dealing with not self-clocking signal formats, that means not only do you have to send the signal format down to the dissonant, but I also have to send a clock cycle with it. So that's 2 pieces of information that needs to go to the dissonant. With this one, RZ polar, I don't. I can send it down to the dissonant without any issues. Why? Because when it gets to the dissonant, it's going to sync up. Bye. I don't need to worry about having to send a clock cycle or additional information. Now there's other advantages and disadvantages of having self-clocking cycles versus the advantages and disadvantages of not having self-clocking signal formats. So let's look at bipolar. Now bipolar is one, if you take a look at the name, bipolar means they're flip-flopping between the +5 and a -5 for logic 1s. Okay? Nothing happens for zeros. This is not self-clocking. However, when you add this in, which is called zero suppression, then it becomes self-clocking. Let's take a look at the bipolar. Well, bipolar does the same thing as neutral. Every time you see a 1, something's going to happen. When we see zeros, it always stays at the 0 line. But in our case, we've logged it in as +5 or -5, and we're going to flip-flop between the two when we're doing bipolar. That's the whole gist of bipolar. So if I was +5 one time, I got to be a -5 the next time I see a 1. And again, you can see in this particular format, there is no self-clocking. It doesn't resemble anything at the dissonant as far as clocking. So I have to send a clock cycle with it. When we go...
Can I ask you a quick question?
Go ahead.
So you said with the last one, with RZ polar, it's always going to be synchronized at the end. Is that because it returns to 0 and it has 0 volts in the middle?
That is correct. It is returning to 0 halfway through the clock cycle. You don't need to send a clock cycle with it because something's happening halfway through the clock cycle.
So then what's the reason that NRZ is the most common if RZ is more efficient?
You have advantages and disadvantages. When you look at NRZ, there is a distinct advantage over others except for CDI. You can run fiber with NRZ better than you can run with RZ bipolar or polar or things of that nature. I don't know the whole inner workings of it. I just kind of skimmed the information, but NRZ seems to be the standard for all multiplexers. Because when it is the easiest, from what I understand, it is the easiest to transfer from one signal format to an NRZ format. Don't ask me why, that's the way the engineers ran it. But I do know this much. Most of the time when it goes out to the distant end is either NRZ or CDI. If it's CDI, nothing really changing. But NRZ normally is on a fiber, which is strange. So it's one of those things where the engineers develop it this way, and they've been able to perfect it to where NRZ is the best solution for everything. Well, I'm not an engineer. I can only give you what I know as far as what I think the engineer was looking at when they did this.
Okay, thank you for explaining that.
Sure. I do my best. I try to research this stuff to where I get an idea of what, get inside the engineer's mind, but sometimes you just scratch your head and nod and still don't understand. But I keep plugging at it. And when you get into electronics like this, when you, let's just say, you're in the development portion of these, it gets very complex with all the formulas and that. And when we get into QAM, holy crap, that is a can of worms that you open up that you just want to put back on and you can't. All right, so far so good. There's only one self-clocking mode that we've gone over, and that is
RZ.
RZ what?
Polar waveform.
Polar. Okay, RZ polar. Everything else is not self-clocking. If it's not self-clocking, what do we need to send with it?
A cycle, clock cycle, something like
Yeah, a clock cycle, clock pulse, a clock, whatever we need. All right, we look at bipolar with zero suppression. This one can be another can of worms, but I'm going to do my best to keep it as simple as possible. It does the same thing as RZ bipolar with a twist. We have something called bit violations. What does it mean? A timing bit is inserted. What does it look like? The last logic one. Now with bipolar with zero suppression, what they end up doing is you can tell the distant end, when you program it into the system, your other system at the distant end also has it programmed in, so you know how the timing is. If you get the timing off, as in you put in one bipolar zero suppression format versus another bipolar zero suppression format, you're going to have major timing issues. Oh no, no. Handy dandy paper here so I can explain that. Alright, so let's look at this. Bipolar with zero suppression. You can say that you can see where the blue arrow is. This is a timing bit violation, and we've got it programmed where it throws the bit violation if there is 4 zeros in a row. What does that mean? It means that I can say it to the distant end, hey, I just had 4 zeros in a row. Here's my bit violation to make sure that we are still synced up. So you can see that we're still doing the 1 halfway through the clock cycle. We're up at +5. The next one will be a -5. So we're flip-flopping here. We get 4 zeros in a row, and like I said previously, it's going to emulate the last logic 1. Notice these two are the same. The distant end knows that there was 4 zeros in a row because if it was a data of 1, this would be plus 5. Would it not? Confirmation there, guys.
Yes, it would have been.
It will be +1.
Yeah, it would be plus 5. If this was a 1, what would this bit violation be? In other words, if this was a plus 5 here, which one would this one be? A plus 5 or negative 5?
+5?
That is correct. Okay, so anytime there's a bit violation, it's going to look back and see what was the last logic of 1 and say, hey, I got to emulate that so I can tell it this is a violation. Because it should have been the opposite. That's that bipolar portion. So this is a reason
Is it
why...
always with 4 zeros?
I'm sorry?
So it just as like a string of zeros. Is that always going to be a string of 4?
Negative. Hence my handy dandy paper that comes, believe it or not, from the NSM. The T1E1 line has 2 different types on it. Bipolar with 0 suppression. The first one is Bravo 8 Zulu Sierra. That's B8 0 suppression. So bipolar 8 Zulu 0 suppression. What does that mean? It means it throws the violation on the 8th 0. This is a North American T1 line. You guys have heard of hierarchy, right? Where you build...
As a general term, yes.
Okay, hierarchy building multiplexers where you got a T1 line, a T2 line, T3 line. We're going to see that in, I think it's 1 Bravo when we get to it. So that's the first one. That's the T1 E1 line on, excuse me, that's the T1 line on the NSM multiplexer that you guys are dealing with. They have the E1 line that also plugs in the same thing. That goes by the name of Hotel Delta Bravo 3, HDB3. This is a European or Japanese, and this bipolar with 0 suppression throws it on the 4th 0. And there's others.
So this one in the example is a European one.
You could say that. You could also say that it was a B4ZS. We also have things like Bravo 6 Zulu Sierra, which is throwing it at the 6th one. We also have a Bravo 3 Zulu Sierra, which throws it on the 3rd 0. That's a T1 line, T2 line, and T... I'm sorry?
Is that going to just be anything we'll need to memorize?
No, this is gee whiz information. And also, if we asked anything that crazy, you need to go to your tech manual, wouldn't you?
Yes, you would.
There you go. So anything that it is, you know, like this, you had to dig for it. And then once I got it, I researched it, and this is what I found out. So you can see that I do my best for you guys when it comes to researching this. That way you don't have to. But if you are still wanting to know, go out on the internet and then ask me, hey, I come across this, I don't understand that, and I will do my best to help you out. Sometimes it may take some research. Other times it's I already know what it is. More, I'll do the research than I already know what it is. But with this, these signal formats are used quite extensively in most of our gear that's out there. It's the reason why we present this to you. Now, so far we've gone through 2 self-clocking formats. What are they?
The 2 self-clocking would be the polar and
RZ polar.
And what's the other one?
RZ. Would it now be the RZ polar zero suppression, I guess?
There you go. So those two. All right, I got,
Can you explain again what that means? Because I was confused on what the self-clocking exactly was.
okay, self-clocking means I don't have to send a clock cycle with it. Are you asking about the bipolar with zero suppression being self-clocking?
Yeah, I'm just asking how self-clocking would be different. Like on this diagram, can you see a difference with it?
Okay, what happens is, remember those figures I was telling you or the numbers I was giving you? Well, that's programmed into the multiplexer. Like you're using that computer to program the NSM. Well, there's, with any multiplexer you can program it. The question is what is that device using as far as a signal format? You may come across these. I know that in servers, when they are having to troubleshoot them, they use this technique in order to figure out if the information is on the server end or they're having problems with the servers. They use the bipolar, just the bipolar, RZ bipolar with the customer end. And we'll get to that in, I think, 1 Charlie. So you see how this plays in together with each other. Did I clear that?
Okay, sure.
No?
Yeah, that clears it up a little bit. It's basically just like a technology that they can add to it.
Yeah, they can. All right, I got 2:08. Let's take another 5-minute break. And I should be finished here in the next, let's say, half an hour with the information we got to go over. All right?
Sounds great, sir.
Sir.
All right.
Yes, sir.
See you at, let's do 2:15, all right?
Sounds good, sir.